Greetings everyone. Today we're going to be talking about equipartition and how this will motivate our study into statistical mechanics. So in a nutshell, equipartition just means that we have a certain number of states, these microstates, and all the different microstates are going to have the same probability. But these microstates will manifest into different macrostates, and those are what we observe. So how does this pertain to this Lego box? So what we see here is that we see a bunch of different colors and shapes, but just focus on the colors right now. So you see green, white, yellow, red, blue. One thing that you'll notice that you don't see is that you don't see a whole lot of colors altogether. You see that the colors are pretty randomly positioned, it's pretty evenly mixed. And the reason why this is, and you can take the Lego box and shuffle it around and then look at it again, and it will look like this again. And basically, all these states are pretty indistinguishable to you and I because they're all this single macro state that's everything mixed up. What's really impossible to see, except when you, first open your Lego box, is that all the blues will be on one side, all the reds will be on one side, the greens. Everything will be unmixed. This is a very improbable state. And basically, after you've opened up and played with these Legos, it will never enter that state again. And the reason why is because of the probability of these states, of these macro states that we are observing. So let's talk more specifically and quantitatively about this. So why should we even begin to talk about statistical mechanics, and why do we care about probability? Up until now, we've been basically applauding Newton for being able to describe so much of the world. Basically, using F equals ma has been a tremendous asset. We can describe what's going on in collisions, we can describe how objects fall, trajectories, we can even describe a lot of fluid mechanics with just F equals ma. The problem with this is these 2 points right here. We'll just start with this one. So if we want to use energy momentum, these Newtonian ideas, to describe the air in this room, we're going to need 10 to the 23 equations, and this is just not feasible. One, because this is way too many equations, and two, because you could never know the exact x and momentum for every single air molecule in this room. It's not going to happen. We can't know these. Even measurably, we can't know these very well because of maybe even quantum effects if we have to bring that up. But even classical mechanics, we can't measure these too well, and it's just not feasible. The other remark is that these Newtonian mechanics doesn't explain this concept of irreversibility, and this will be the last thing that we talk about today. So this Newtonian approach fails these 2 points right here, which makes it impossible for us to talk about the air in the room and these big systems of everyday life. How are we going to use this statistical approach, and what are the assumptions that we're going to make? Basically, our endpoint is going to be this PV equals nRT, which you may be familiar with. This is the ideal gas law. So this is where we're aiming at, and we're going to have to take a little bit of a route to get to this point, and how do we know that this works? So our very first thing that we're going to talk about is basically intro to probability, and we're going to do this with a coin toss. And the reason why this is a good place to start is because there's only 2 states here. We just have heads and tails. So it's really easy for us to be able to describe all the different states for a 2 toss system. So if we toss 2 coins, we can either end up with 2 heads, 2 tails, or a head and a tail and a tail and a head. So these are the only possibilities that we can end up. So if we want to split these different states, these are all micro states. If we want to split these up into macro states, so what macro states, how they're different is that this just looks at states that have 1 head. Basically, we're saying we can't tell the difference between this and this. These both look the same. They only have 1 head. So this state is actually more probable than entering a state with 2 heads or 2 tails. because there's two states that look like this. So we're going to move on to a slightly more complicated example next. So now if we look at a system with 4 tosses, we have to do a bit more work to find out all these different microstates. But essentially we end up with just 5 macrostates. So this isn't a whole big difference between 2 tosses with the number of macrostates, but the number of these microstates is really exploding. And a real easy way to get there is that since we have 2 states and we have 4 tosses, this is going to give us our total number of microstates. So this is kind of an easy way to work it out without basically emptying your pen trying to figure out all these different combinations. So the one thing that you'll notice is that right here, again, this 2-head system, the one that's evenly heads and tails halfway, is the most probable state. The ones that are least probable are these 4 heads or no head states, which are the least probable states. So here we only tossed 4 coins, and we're going to increase the complexity of the problem again. So now instead of coins, let's look at particles, because this is really what we're more interested in. So let's say that we have 6 particles, and they're in this box, this outside box here. And we want to know what is the probability of getting all 6 of these particles on just 1/2 of the box, basically. So we know that if we just let the system evolve, you might have a state like this. And so there's 3 on one side, 3 on another. This would be our most probable state, and you would guess that just out of intuition. And you would guess this is a less probable state. So how do we get the probability? Well, what we need first is the total number of states. The total number of states that we can have is we can put, particle A over here, and then particle B, C, D, E, F over on this side, and then now move each particle over. So we could go through this very tedious exercise, or we can just know that each particle can be on this side or this side. So there's 2 states for each particle. And then there are 6 particles, so that gives us a total of 64 states. What is the probability of having all 6 on one side of the box? And so here's our total number of states, and then the number of states that look like this with just 6 on one side, there's only one arrangement of that. So that's just 1 over 64. So in this example, we have a 6-particle system, and the particles can be on 2 sides. So again, our total number of states is, again, 2 to the 6, which is 64 states. But now, instead of having all 6 on one side, now what we care about is having 3 on one side on just the left side of the box. So we could try to figure out the total number of states that look like this. So probably the easiest way to solve this visually is just by looking at which particles can be on this left side of the box. So if we just look on the left side, we can have particles A, B, C, and then we can have particles A, B, D, and then particles A, B, E, particles A, B, F. So these are all the A, B states that we have. And then for states with AC, now we have A, C, but we can't pick A, B, C again. So we pick A, C, D. We can't double count the state. And then we pick state A, C, E. And then the next state that we have is we're going to pick A and D together. And then since we already have C, we can't pick that guy again, so we're only left with E. So for state A being on this side of the box, we have 1, 2, 3, 4, 5, 6, 7. So there's basically 7 states that have A on the left. And then now we have to do this again for state B, and making sure that we don't have double counting at all. So there's actually a really easy formula that will do this for us, and the way is that you have n factorial. So this factorial, what it means is that, let's write it up here. So n factorial, let's just say that n is, is 4, okay? So this would be 4 times 3 times 2 times 1. So basically you just multiply everything down until you get to 1 on this n factorial. So this formula is going to be n factorial all over n minus k factorial times k factorial. So this looks really strange, but if you've taken any probability class, you'll have seen this, and it's called n choose k. And so this basically does this algorithm for us, so we don't have to do all this exercise. And what you'll get is that you'll get the total number of these states, and I think it's 20 if you work this out. So then n here is going to be that we have 6 particles, and then now k is going to be, we're choosing 3 to be on this side. So it'd be 6 factorial divided by 6 minus 3, which would be 3 factorial times 3 factorial. You'll end up with 20. But 20 is not the probability. This is just the number of states that we have that look like this. So if we want the probability, we need to take this 20 and divide it by our total number of states. So our probability is going to be 20 over 64. So now I want to help motivate why this is so important with some bigger numbers. So you're going to see me use this n choose k equation again. So basically here we are, and I'm looking at all the different states that we could have. What is the state that we have 3 on the left side? So that's the one that we just did. So that's just 20 states. And the probability is 0.3. So 30% of the time we're going to expect to see this state. And then we could look at the system with just all 6 on one side. So that's this state. And we could look at 5. We could look at 4, 3, 2, 1. So these are all the different states that we can have, and we accumulated all the probabilities, and we plotted it, and it looks like a nice normal distribution here. What I want you to notice, though, is that 85% of the states of this system lie within 3 plus or minus the square root of 3. Now this square root of 3 it comes from our sigma of this distribution, so the width. The mean of this distribution is always going to be at this n over 2. And this is going to be our most probable state. We're going to have half on one side, half on the other side. But then the width of this is going to be square root of n. Square root of n over 2, actually. So we're going to look at how this distribution changes with n. So now we can look at what our system would look like if we had 12 particles instead of 6. So you'll notice that our distribution is functionally the same. But what's really interesting is that now for having 12 particles, our mean is at 6. So then the width of our distribution is a square root of 6. Square root of 6 is about 2. So basically between here and here is 85% of our states. And so this is not much. Basically, you're never going to see less than, n minus 3 particles on one side. So these states that are 12 on one side are are very not likely to happen. Alright, so even more so. So we looked at 6, we looked at 12, and now I'm plotting what's going to happen for 24, 48, 1,000, and 10 to the 23. So this is basically the number of molecules in 1 liter of gas, the air in this room. So for even 1,000, you would expect 500 to be on the left side, and then 85% of our states are going to be between 480 and 520. So the fluctuations of this are not very big compared to the size of n, and that's what this W over n I'm showing is. So basically, the width of this, how much this can fluctuate, is like 5%. So then we can look at 95% of our data is just a little bit bigger. And basically all the states that we're going to find are going to be even number of molecules on one side than on another as soon as n gets large. And when n gets thermodynamically large, like 10 to the 23, the width, while it's really big, 10 to the 11 is a huge number. But compared to 10 to the 23, it's minuscule. So basically, the width over the mean is not 5% anymore. It's 10 to the minus 12. So this is incredibly small. So if you expected to see anything more than 10 to the 11 particles more on one side of the room than on the other, this would happen less than 1/10,000th of the time. So basically, if you ever expect the density of the air in this room to fluctuate measurably, it's never going to happen. It could happen. It's not impossible. But you're going to have to wait the history of the universe for this to ever happen again, basically. Where this comes in really useful is how to understand what's going on in a gas. Like I said, and this all refers to this equilibrium state. These are our most likely states. We know that we have a bunch of gas and a volume, that the most probable state is going to be one half of the gas on one side, one half of the gas on the other side. So let's say we took a box here that has gas only on one side. We've got a partition here, and we pull the partition out. What's going to happen? We know that the gas is going to expand and fill up this vacuum. And what happens then is that the gas expands to fill, and now the density of the gas is 1/2 what it was before. But one thing that you'll never expect to see is that this system right here that's full of gas to ever go back to this state. These air molecules are never going to just bounce back and all end up on one side of this container at some point in time. It could happen. It's not impossible, but it is so improbable that it is never going to happen. And this is what we mean by irreversibility. So when we take a partition out of a gas and let it expand, this is an irreversible reaction. And this is one of the things that cannot be explained by these Newtonian mechanics. So we're going to be talking more about all these ideas in class and how to estimate probabilities.